Hi, my dear friends. In this session, we are going to discuss about long transmission lines. So, before going to start with the long transmission lines, uh, in my YouTube channel, I have uploaded the explanation regarding a short transmission lines and medium transmission lines with three different methods. So, to understand this, we have to go for last two transmission line, that is a short and medium transmission line. And here the long transmission line is nothing but here the length is more than 150 kilometer. Length is more than 150 kilometer. So it is well known that line constants of the transmission line are uniformly distributed over the entire length of the line. However, reasonable accuracy can be obtained in line calculations for short and medium lines by considering these constants as lumped. If such an assumption of lumped constants is applied to long transmission line which is having the length will be more than 150 kilometer, it's found that serious errors are introduced in the performance calculations. Therefore, in order to obtain a fair degree of accuracy in the performance calculations of long lines, the line constants are considered as uniformly distributed throughout the length of the line. So help use a method for a long transmission line is a rigorous method, that is a rigorous mathematical treatment, so which requires for the solution for such kind of long transmission lines. Before that, just look at the diagram. So this is a long transmission line. So here, uh, which gives the equivalent circuit of a three-phase transmission line on a phase neutral basis. On a phase to neutral basis. If you're considering this as a phase and this will be the neutral, that is all the values will be line to line values. The whole line length is divided into n sections, that is a number of sections, n sections, each section having a line constants, each section having the line constants, that is R and XL, with respect to C will be having 1 by, that is a 1 over n, that is 1 by nth of those for whole line. So the following points may be noted. So now just look at this point 1. The first point is the line constants are uniformly distributed over the entire length of the line as it is actually the case. That is, whatever the line constants you have, that is R, L and C, will be uniformly distributed. And as we discussed in the line constant RLC, the R and L, that is a resistance, and XL, that is a resistance and inductive reactance, will be always connected in series. Just look at that, will be always connected in series, whereas the susceptance leakage susceptance is denoted by capital B, and a leakage conductance can be denoted by capital G. Are shunt elements B and G. Just look at here the shunt elements, that is a leakage susceptance and the leakage conductance will be the shunt elements. The leakage susceptance, the leakage susceptance is due to the fact that capacitance exists between line and neutral. The leakage susceptance due to the fact that the capacitance exists between the line and the neutral. Similarly, the conductance, the leakage conductance takes into account the energy losses occurring through leakage over the insulators. This is taken into the account the energy losses occurring throughout, that is occurring through leakage over the insulator or due to corona effect between the conductors. So that the admittance, we can write the admittance, that is admittance is denoted by Y, or else you can is given by the square root of G square plus B square will be the admittance. So the last point, the leakage current through shunt admittance is maximum. The leakage current flows to the shunt admittance is maximum at the sending end of the line and decreases continuously. The leakage current will be decreases continuously at the receiving side, that is at the receiving end of the circuit, is approached at which point its value is 0. Okay, so the analysis of a long transmission line, we can also call this as a rigorous method of analysis of long transmission line. The circuit diagram shows here that one phase and one neutral connection, one phase and one neutral connection. So here with the impedance and shunt admittance, that is, which will be having the impedance Z is nothing but R plus JXL, and the shunt admittance will be having, that is, SG or else Y. So here just consider a small element in the line of length dx, small element in the line of length dx situated or else placed at a distance x, placed at a distance x from the receiving end, x from the receiving end. So let us consider some notations. You have to know what are the naming of the notations here. A small z, so the z is nothing but here series impedance of the line per unit length. Similarly y, this y is nothing but shunt admittance of the line per unit length. Similarly capital V, so capital V is nothing but voltage at the end of element towards receiving end. Then V plus dV, voltage at the end of element towards sending end. Then I plus dI is nothing but current entering the element dx, current entering the element dx. Similarly capital I is current leaving from the dx, so this is the dx, current entering to the dx is I plus di, current leaving from the dx is I. So then for the small element dx, just look at the circuit once. A small element dx which has a length x from receiving end, and I plus di is current entering to the dx and I is current leaving from the dx, z is a series impedance and y is the shunt admittance. So here then for small element dx, for the small element dx, z into dx is nothing but, so this z into dx is nothing but series impedance. Similarly y into dx is nothing but a shunt admittance, so that I can write small change in voltage dv is nothing but I into z dx. v sorry dv, the small change in voltage at sending end we can write as I into zx, I into z into dx. So we can write here, I'll repeat, change in dv we can write as this is nothing but I into z dx. Okay, so now go for the analysis.